Hello students, welcome back. Let's go to section 4, and this is rather special. I don't write these kind of problems a lot, but our textbook does consider this. And if you want to specialize in science or engineering, especially engineering, then you gotta know this. Okay, let's begin. There's something called initial condition or initial value condition, and that's used to determine plus c. Let's begin with integrand 2x and take the antiderivative. We get x squared plus c. And plus c can be arbitrary, so we do not have a unique function. But if you have an initial condition, say f of 0 is 0, f of 0 is -1, f of 0 is, say, 25, or in this case, instead of starting from 0, you're starting from -1 for some strange reason. Maybe you're starting from data from yesterday, I guess. F of -1 is 3. All these kind of things are called initial condition or initial value condition. From those, you can determine c. How do you do that? Well, you see, f of x is x squared plus c, right? And then f of 0 is 0, so squared plus c is 0. From there, what do you get? 0 squared is, of course, 0, so c is 0. So if c is 0, it just drops out. And then that's what you get. What if you have f of 0 is -1? F of x is x squared plus c, but the initial condition says f of 0, which is 0 squared plus c, is -1. From there, you can deduce that c is -1. You see, c is -1, this is 0. So plugging in -1 in place of c right here, you get this answer. You have only one such function. Here's another example. If you have f of x is x squared plus c, yeah? And then let's apply the initial condition. So that is -1 squared plus c is 3. We have to actually solve this equation this time. 1 plus c is 3, so c is 2, flipping 1 to the other side. Okay, c is 2. Yeah, this is 2, so plug in 2. That's how you get x squared plus 2. This way, we can determine your function. This kind of things are initial condition, and these kind of problems are called initial value problems. Here's some examples of initial value problems. Find the original function when the derivative is like this. And then you can use this initial condition. Well, basically, you're determining plus c. So your f of x is the antiderivative of 3x squared plus square root of x. Let's rewrite this square root of x into 1/2 power. Okay, let's find out the derivative, antiderivative, excuse me. 3 was there before. X to the 3rd power and divide by 3. Okay, there you go. And then next, add 1 to the power and then divide. And then what do you have? You have plus c. That's your antiderivative function in the general form with plus c, but there are infinitely many candidates here. This initial condition will reduce that into a unique function. So let's apply that. F of 1, which is plugging 1 here, what do you get? This is 1 to the 3rd power, and this one is 1 to the 3/2 power. So what do you get? 1 plus 2/3 plus c is, you see, f of 1 is 1/3, so that's equal to 1/3. You can solve this. What do you get if you solve it? 5/3 plus c is 1/3, so you're getting what? Negative 4/3, is that it? Is that it? 1/3 minus 5/3. So negative 4/3. But be careful, this is not the answer. This is not the answer. Answer is right here. You want to find out f of x, so right here, where c value is now determined. So you can write your final answer like this. Therefore, f of x is, let's copy and paste this one. That's the antiderivative function, except that the c value is now determined as 4/3. Negative 4/3, excuse me. So that's how you do it. Antiderivative, put it into initial condition, solve for c, and you get the answer for c. Alright, that's the answer for c, not the answer for the problem. Plugging in back into this, we get the answer to the problem right here. Antiderivative, that's step 1. Step 2, apply the initial condition and solve for c. Plug it back in, and that gives me the final answer. Time for another? Probably not. Here's a problem. Go ahead. A little bit harder integral problem here, but you should be able to handle it. Hold on. Let's check. Step 1, antiderivative. Take the antiderivative, and then power form, and then we use the antiderivative. Remember, we have this 1 over a popping up, 1 over a popping up. Okay, after some simplification, we got this. Next, initial condition. Plug in x equals 1/2, and then run it. That should be equal to 1/2. You see, this value 1/2. So let's simplify this. Square root of 4, 2. So 1/2 e to the 0 power. So 2 minus 1/2 plus c is 1/2. 3/2 plus c is 1/2. C is negative 1. And that's going to go right here. Alright. There are some more initial value problems. This time, okay. This one's pretty much okay. Take the antiderivative. This is a trigonometric function. And then x of 0 is negative 1. From there, you can determine c. Now, this one is going to be a little bit different. We have second derivative. So if you take the antiderivative, you're going to get first derivative x prime. And then plug in an initial condition. You can determine an integral constant c. Take the antiderivative again, then you're going to get x of t with the second integral constant. So you need another initial condition. You see, you have to take the integral twice, antiderivative twice. So you have 2 integral constants, 2 unknowns. So we need 2 equations. First equation here, second equation there. Here we go. Antiderivative. Happy with this? Okay, plug in t equal to 0. And the answer should be negative 1. And solving for c, you get c is -1/2. Satisfied? Stop the playback and do your computation if this is too fast. So plugging this back into the original equation, you get the final answer. By the way, this expression is extremely important in physics. It's called harmonic oscillator, and it's used for spring motion and things like those, and also for electric currents, alternating currents. How about this? Well, take the antiderivative, all right. Another antiderivative, okay, so we get x of t, and you see the c became ct, and then another one d. And then let's use these two conditions. We have two unknown variables, c and d, so we need two equations. X of 0 is -3. Okay, plug in t equal to 0 right here. And I set it equal to -3. So, c times 0, so c disappears, and we get d value directly. We are lucky. Most of the time, you're going to get just two equations and two unknowns, and you'll have to solve a system of equations. Next, we use this one. So from here, plug in t equal to 0 and run your computation. C is 4. So plugging those back into this, you're going to get the final answer. X of t is like this. So we can use the integral twice because we started from the second derivative. As for boundary value problems, oh come on, this is... Oh, we do have some time. Okay, alright, let's go ahead and do that. Take this antiderivative twice because this is starting from the second derivative. So antiderivative number 1, so x prime, another antiderivative, so we get x of t. And then we use boundary condition. X of 0 is -3, x of pi is -1. So we are putting both of them here. So we have plugging 0, we get this. Plugging pi, we get that. And again, this problem was set up kind of nicely so that we get d value right away. And then we get c value like this. We are lucky. Usually, you're going to get a system of equations with two unknowns and two equations. And then you have to go from there. We are just lucky. In any case, from these two equations, we get c and d values. Plug those back in, and we're going to get the conclusion. This kind of things are called boundary value problems because at the boundary, t equals to 0 and t equals to pi, and then typically between 0 and pi, we get some solution. The others are called initial value problems, and those are the only cases that you have to work on, the integral constant plus c. Otherwise, I'm not going to care too much about plus c. I'll stop here. This one here, no, I'm not going to reduce it into an optional topic. Very close to optional topic, but our textbook author still places some emphasis here, so let's keep that. If you're going to go to an engineering school or something, some physics or chemistry major, maybe this is important.